Welcome to our today's lesson, Understanding Voltage for Warehouse Workers. Objective: to provide a basic understanding of voltage using relatable analogies and simple explanations, enabling warehouse workers without prior scientific knowledge to grasp its concept. We begin with focusing on the diagram of a battery displayed. Keenly note the two terminals marked with positive and negative signs on the two ends. The two ends are designed to have high electric potential energy on the positive end and low potential electric energy on negative end. This situation creates a difference in potential electric energy on the two ends. This difference in electric potential energy causes electrically free charged particles in an electric conductor connected at the two ends of the battery to move from high to low potential points. It amounts to electric force, known as electromotive force, EMF, also called voltage of the battery. The moving charges in the conductor is called electric current. Let us listen to an explanation and watch this video clip on YouTube to understand how the EMF drives current in an electric circuit.
In a simple electric circuit, these four vital components can consist of battery, copper, switch, and a light bulb. Each play a significant role in producing electric current. The battery is the energy source. It supplies the required electromotive force to cause the electrons to move in the circuit away from its negative terminal and pulls them towards the positive terminal. It is the provider of voltage, not electrons as many would think. The copper is the conductive path, which provides a pathway for electricity to pass through it with greater ease.
To relate the flow of electric charges, or electric current, to water flowing at a waterfall or water current. Now focus your attention to the animation of the waterfall and compare it with the animation of electric charges on the side. What can we see to be common? 1. Water on one end is raised, high gravitational potential energy, then low gravitational potential energy on the other end. This is same as the electrical system shown also with both high and low electric potential energy ends. 2. In both cases, there is flow of particles from high energy potential to low energy potential. 3. There is a complete path through which particles in each system flows. In electrical system the path is called circuit. What is different in the two systems? 1. The force driving water to flow is gravitational provided by the Earth's gravity, while in the electrical system the force is provided by the chemical energy in the battery. 2. Motion of water particles takes place in the waterway while motion in the electrical system takes place in the conducting cables known as the circuit. Water analogy. We are going to relate the flow of electric charges, current, to water flowing in a waterfall. Now focus your attention to the animation of the waterfall and compare it with the animation of electric charges on the side. What do we need to know about molecular composition of water? Let us focus on the animation showing water molecules in motion and electrons moving in a wire. Observations and explanation. 1. Just as water is made of tiny particles, molecules, electricity is made of tiny charged particles called electrons. 2. When voltage is applied, these electrons move through the wire, similar to how water molecules flow down the waterfall. 3. This movement of electrons creates an electric current, which can power devices and machines. Points to note. The following points should be underscored. 1. Electromotive force, EMF, is the push that causes electrons or charged particles to move, similar to the force of gravity on water. 2. Voltage is essentially the measure of this electromotive force, EMF. It tells us how much potential energy is available to move electric charges, much like how height tells us the potential energy available to move the water. 3. A higher voltage means a stronger push, just as a taller waterfall means a more forceful flow of water. The level of voltage determines the strength of the electric current, which may be useful in doing the intended work or cause damage such as burn up the devices. 4. No electric current flows across points on the circuit at equal potential electric energy levels. This is the reason birds stand comfortably on high-voltage electric cables. 5. Earthing of cases and handles of devices sets their electric potential energy levels at 0, equal to that of the earth. It is for safety reasons that electrical devices we handle in warehouses and at home are properly earthed. We are going to further illustrate the concept of voltage with a car climbing up a hill and then rolling freely downwards. Imagine a car that needs to get from the bottom of a hill to the top. What does the car need to climb up the hill? What is it in the car provides it? Watch the animation. To achieve this, the car's engine must do work to drive it uphill. This uphill journey represents the energy input necessary to move the car against gravity. In electrical terms, this energy input is similar to what a battery does when it creates a voltage, or potential difference, across its terminals. The battery acts like the car's engine, providing the energy needed to move electric charges through the circuit. Here we can see how voltage of the battery raises the potential energy level of the electrons, which are then set into motion to the points of low potential energy level in the circuit. Similarly, we see how the engine of the car lifts the car up the hill to a point of high gravitational potential energy. Once the car reaches the top of the hill, it has stored potential energy due to its elevated position. Likewise, the charges in a circuit have potential energy due to the voltage created by the battery. When the car is allowed to roll back down the hill, it converts its potential energy into kinetic energy. Similarly, when charges move through a circuit, they release energy to do work, such as lighting a bulb or powering a device. In this analogy, the electromotive force, EMF, is the force provided by the battery to drive the charges uphill, just like the car's engine drives it up the hill. The descent of the car, or the flow of charges through the circuit, represents the energy being used to perform work, like lighting a bulb, akin to the car's kinetic energy as it rolls downhill. Summary. Voltage is like the height of a waterfall, determining the potential energy available. It pushes electric charges through a circuit, similar to how gravity pulls water down a waterfall. Understanding voltage helps us see how electrical devices are powered and why they need a certain push to operate efficiently. Knowledge of voltage enables us to understand principles of conservation and transformation of energy. Points to discuss. Question: what questions do you have about voltage or how it works in circuits? Next step: would you like to explore more about how voltage relates to other electrical concepts?